In the second video arkadaşlar, I would like to talk to you about two important things, okay? One of them is representing any x of n using Dirac ends. What did I tell you in the previous video? Any signal can be represented as a linear combination of time-shifted versions of Dirac n. What does that mean? If my x of n is this, for example, this is -1, 1, and 2, 1, and this is my x of n, this is 1, this is 2, this is 1. How can I represent this using Dirac ends? X of n is equal to Dirac n plus 1. This is n plus 1, right? This part. And then plus 2 Dirac n plus Dirac n minus 1. This is Dirac n minus 1. This is 2 Dirac n. So I can represent any signal like this using linear combination of shifted versions of my impulse function. Okay? So this is critical. If x of n is my input to a system which has an impulse response of h of n, then my output y of n will be equal to h of n plus 1 plus 2 h of n plus h of n minus 1. So what am I saying here? If I know the impulse response of a system and I can easily decompose my input signal into Dirac ends like that, I can easily find out the outputs, okay? The outputs will be linear combination and shifted versions of h of n. If we know h of n, let's say h of n is this, okay? This is 1, this is 2, this is 0, this is 1. This is my h of n, let's say arkadaşlar. How will I find y of n for this input? I will come here and write h of n plus 1, which is shifted to the left, minus 1, 0. This is what? H of n plus 1. Then I will have h of 2h of n. That means I should multiply everything by 2, keep the times as they are. Okay, now it will be 2 and 4 at 0 and 1, which will be 2h of n. And then now I will also add shifted version of h of n to the left. Okay, this is 1, this is 2. Now this is 1. 0 is shifted to 1, and 1 is shifted to 2. This is now something that I will use for finding the output, which is y of n. Okay, now I will add at minus 1, I have 1, 0, and 0, right? Minus 1. I'm adding all values at minus 1 coming from these three h of n's, okay? So minus 1 is 1. How about 0? I'm not looking at this h of n anymore. This was h of n. Now I'm working on these three things. At 0, I have 2, again 2, and 0, which means 4. Okay, this is 4 at 0. How about 1? Nothing here, 4 here, 1 here, totally 5. I will have 5 at 1. And then nothing here, 2 here. I will have 2 at 2. And other than that, I don't have any any other values. Every other value is 0. Okay. So if what am I saying here? If I know the input, and if I know h of n, if x of n is given, and h of n is given, what should I do? I should decompose this into Dirac n's, and then apply this Dirac n to my system, and I will obtain different like h of n's, edit versions of h of n's with some time shifts. Then I will add them up and then obtain my y of n. Okay, so this is a kind of using the linear time invariance property of finding h of n. Okay, using h of n, I'm trying to find out the output y of n if I know x of n. Okay, this is one critical thing. As you remember, what did we do right now? We have performed some shifting, and then we have done some addition. Arkadaşlar, at this point, I have to say two things right now. One, I can write x of n as this linear combination of Dirac n's. I will first write and try to explain this to you. Okay. So what am I writing here? This is the basic understanding of convolution. And I want you to understand this basic representation so that you will understand convolution operation on signals. This is the first time maybe you will hear and see this property or this concept of convolution. In Turkish, we call it katlama. Okay, we will use this in many parts of this subcomponent. So I want you to focus on this part a little bit more. What does this x of n is equal to summation of x of k times Dirac n minus k? If you remember, we had this signal, right? We had this signal. This is like 1, 2, 2, and 1 at 0, minus 1, and 1. So what did I do here when I was writing this part? What did I do? I looked at the value of x of n, which is 1. Okay, 1 times, where is k? Okay, where is k? At minus 1. So instead of k, I will write minus 1, and this will be Dirac n plus 1. And then I will go to the next one. What is my x of k? What's the amplitude of that signal? Plus 2 times Dirac, k is 0. Then I will have Dirac 0. Plus, now I'm here. What's my amplitude? 0, 1. And then I will write 1 times Dirac n minus 1. Okay, Dirac n minus 1. So what do I have here? I can write x of n using this summation rule. If I had more signals here, more amplitudes at different time instants, what would I do? I would add more k's to my addition, to my summation, and more shifted versions of my Dirac delta function. Okay, if you remember, this was Dirac delta function. So what am I doing here is I am having shifted versions of Dirac delta function. So this is something important for you, arkadaşlar. Let me move one step further. And here, how did we write y of n? How did we write y of n? We have written, as you can see here, we have written y of n as shifted versions of h of n, right? So what can I write here? What can I write here, arkadaşlar? So the output will be summation of k from minus infinity to plus infinity x of k times h n minus k, right? So what did I have here? What did I have here arkadaşlar? X of k. What was it? What was it? 1, right? X of k, 1 times h n plus 1. Why is it n plus 1? Because k is minus 1. What is 2? It is coming from this one. Why is this is h of n? Because it is k is 0. This is minus 1 because my k is 1 and the amplitude of that signal at that sample is 1. So I can immediately write this function, write this formulation like this arkadaşlar. Okay, and let me change the color here, and I will write this is convolution sum. Okay, convolution sum. What does it mean? I have an input to my system. I have my impulse response. I will have a special operation. It's not simple multiplication arkadaşlar. It is not simple multiplication. I'm not just multiplying. It's not simple multiplication. So I should remind you of this is not a simple multiplication, and we should be careful about this property of convolution sum. What does it do? I should have my x of n, replace all n's with k, and then I will have my h of n, and then do some multiplication between them and do the summation. Okay, this was the again another fundamental part of convolution sum, which is dealing with finding the output using the input and the impulse response.